Inventions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
Hey everybody, oh my gosh, class is over. What are we doing? Tara, good to see you here. Who all is here currently? Let's do some work. It is time for some work. We could do some chapter 19. We did chapter 17 a lot yesterday. Shannon, good to see you here. What is it time for? What work is it time for? I'm pulling up my Pearson here. What work is it time for? You tell me. Chapter 17 quiz? What do you want to do on chapter 17 quiz? Which questions on chapter 17 quiz? What questions shall we do? Oh yeah, I'm battling a little bit of a sore throat today. Hopefully everything goes smoothly in that way. Can we do question one? Question one, Grant, on which thing? Sugar and cereal? Yeah. We did that one at the end of class, but we can do it right here too. Sugar content in cereal. That one is going to require jump. So let me get my jump going. That one requires jump. JMP. That one requires jump. Jump constantly asks me for my license. I don't know why. It is what it is. The sugar and cereal one. A new approach for teaching mathematics was introduced. Is that the CPMP one? We can do that one. The chapter 17 quiz numero uno. But so Grant, thank you so much for asking. Grant, let's do some points right here. Everyone's quiz is different. So the start of the question. Some crazy points in the chat. Everyone's quiz is different. So your quiz will be a little bit different than everyone else's. So you'll have different questions. So let me know which one you're working on, and I'll find that right here. We're gonna do the sugar content and cereal one to start right here. The core plus mathematics. The box plot one with rocks. Cool, we got 3 questions to go here. Okay, so let's go find these questions. We got some sugar content and cereals. So we'll start off with the sugar content and cereals. Now, what do we need to use to solve the sugar content cereals? New approach? You bet. To solve the sugar content in cereals, how do we do it? How are we going to solve this one? I'm going to show it here in a second, but how would we solve it? How JMP is going to help solve it. Trying to find it. Here we go. Okay, I got the question. JMP. Right. So here we are at 4th out of 3. Stat 201, chapter 17 quiz. Let's go do it. Here we go. And so for this question right here, when we do a 2-sample T, what are we comparing? There's questions on the test that ask you to understand, like, what are you doing? Can anyone explain to me, we are about to compare the what for children's cereal and the what for adult cereals. With this problem right here, we have 2 samples. We took children's cereals like Lucky Charms, Fruit Loops, Rice Krispie Treats, and then we took adult cereal like Fiber One, Cheerios, Life, all the not fun cereals, and we are going to compare the what. People are saying means. We're going to compare the means what's. The mean what's of these cereals. You are right. We're going to look at the difference in means, and we're going to estimate the difference in means of the what. The difference in means of what? Of the average this for sugar, for the average this for cereal for children, and the average this for adult cereals. The mean sugar content. So we're going to look to see if there's a difference. Does that make sense? We're going to look to see if there's a difference, and it's the context, right? We're going to look to see if there's a difference between how much sugar the average cereal for children has and how much sugar the average cereal for adults has. That's the point of this question, to be like, which of these has more sugar in it? Which, just look at the numbers, 51, 43, 44, 43, 8, 9, 13. What do you think is going to come out right here? We're going to find that, generally speaking, children's cereal has more what? Like when you look, just looking at the data, it points in this direction. We're going to do the analysis, but looking at the data, it seems pretty clear that what? Like I'd be looking at the data and be like, seems to me that what? Just looking at the data, like this cereal had 42 grams of sugar, 57, 46, 41. It seems to me in this, the adult cereals have like 4 grams, 7 grams, 4 grams, 24. 24 is a lot for an adult cereal. It seems to me that children's cereal generally has more sugar in it. So we'll take a look right here. Does that make sense? The researchers actually took the cereal and measured how much sugar is in a serving of it. So let's go ahead right here and copy to clipboard. Now that we understand what we're doing, we're going to copy to clipboard, and then we're going to hit Control C. Now, when you're inside of Jump right here, you want to go to File, New, Data Table. File, New, Data Table. Under File, New, Data Table, do not click inside of it yet, and you want to make sure for this one to paste with column names. How do you know you've done this properly, which properly is done on the left over here, and not properly is done on the right? How do you know by looking at this you did this properly and pasted quantitative columns? How do you know you did this properly? And so you want to look at this when you paste the data. And if you did this, if you did an error, restart, start a new sheet again. How do you know you did this properly? A lot of people have this problem right here and they say, it won't work. And I say, wait, you didn't do it properly. The correct way is on the left. Yours should look like this. This is the wrong way over here on the right. How do you know you've done it properly? Because the variable type over here, the column names have changed. Well, and great job, Jensma right there. The columns are blue, and that means quantitative, continuous. And over here, they are nominal. You have the blue exactly, quant versus cat. So this is the wrong way. If you do that, restart and repaste with column names. So now we're going to go here to tables and stack. Tables and stack. Once you go to table stack, double click both of them and stack both of the columns right there. Now what this is going to do is it's going to stack both those columns on top of each other so that you have a what variable and you have a what variable, which is the point of doing the two sample t. The two sample t means you have a two-level what variable and a quantitative variable. So what do you have to do the two sample t? The two sample t means you have a what variable over here and you have a what variable over here. The two sample t means you have what kinds of variables. These are important notes to take down when you're doing the two sample t. You will have a two-level what variable, a two-level categorical variable, and then you will have a quantitative measure that you're comparing between the groups. So we're going to look at the mean between the groups to see if there is a difference. To do this, we're going to go to Analyze, Fit Y by X, because we have a Y variable, the data, which is quantitative, and we have an X variable, the label, which is categorical. So now we're going to go right here and put the label to see if the label can explain why the data is the way it is. Does the label explain, the label of the cereal, explain the data? Take a look at the x-axis. You see the label on the x-axis. And one thing we often like to see for this are side-by-side whats. Now, this is not the answer to the question. Yeah, it explains, right? So a way to visualize this is with side-by-side whats. The way to compare two groups on a quantitative measure is to visualize it with side-by-side whats like your project. To visualize it with side-by-side whats. This is not the answer to our question yet, but side-by-side, great job right there, Jansma. So excellent, we're going to throw some more points out. Side-by-side box plots. So side-by-side box plots are the visualization of comparing two groups on a quantitative measure. Adult cereal, children's cereal, two sample, quantitative T. So when we do Mr. T, he's quantitative because he's mean if you're doing drugs. So now we're going to go over here to the t-test. Now, you might think we're doing a t-test, but when you do the t-test, you also get a t-what. You also get a t-what. What is this right here? The upper CL, lower CL for the difference. That is the what for us. It's the bounds, also known as the upper and lower for the what. What is the C? That's probably confidence limit, but this is your what right here. Important to know what this is in the output, because I think the true difference between the sugar content is somewhere between 31.39 to 39.92, and we have evidence that children's cereal has more sugar than adult cereal, probably in this range. This is a confidence what? This right here, the upper and lower, we might have some graphics from this, is the upper and lower bounds for a what? That is the upper and lower bounds for a what? That is the upper and lower bounds for a what? For a confidence interval, or the confidence interval. So that is the upper and lower bound for the confidence interval. And what is at the very center of this interval? Like if you were to average those numbers, the center of the interval is the what? So you see that value right there? This is a different interval, but it works the same mechanically. That if you average these values right here, the upper and lower number, at the very center is going to be the estimate, which is the difference. That's the center of the interval right there. So you can take a look at ours. You have to see how 35 is at the center. Someone just do a quick guesstimate of the margin of error. This is a good practice. We're doing a lot of review for the test right here. I don't want you to find out the margin of error exactly. I want you to round that to 35, and I want you to say 35 plus or minus something. If you understand it this way, you can probably find out the exact margin of error, but just say 35 plus or minus what for the margin of error. If you understand this output, we're practicing knowing that this is the center of the interval. And so 35 plus or minus what? Don't solve it out exactly. Just be kind of rounding the numbers and be like, it's 35 plus or minus what? The margin of error is what we have to go up from the center to the top and down from the center to the bottom. So 35, and just round it. Don't worry about the decimals. I just want you to say 35 plus or minus what? We're making sure we understand what this output's showing us. 35 plus or minus what? Don't worry about the decimals. 35 plus what? 35 minus what? What up, Charlie? Oh, Blake did a great job right there getting more accurate decimals. Blake did 4.2. And think about this, 35 plus 4, which is what I was going for right there, is equal to 39. And 35 minus 4. So if you want to find out the exact margin of error, 4.3 about, right? You could go right here and do the following. You could go the upper. I remember we said it's about 4. So there's the exact, Blake. So was your estimate of about 4.2 pretty close? So we took the distance. The difference is from the upper. Took the TEC exam. Let's throw some 10,000 more for TEC right there. Thank you. Great job, Charlie. Good exam right there. I hope you did well. I have good faith in your abilities, Charlie. I think you probably, that's my thoughts on it. I have faith in you. And we've answered the question right here because, and Charlie, does the TEC cover a lot of the stuff we do in like 201 and how to use these things? Because confidence intervals are very important to know how to use. The 2 sample T went really well. Nice. So 31.40. Does it say 95? Does say 90. Oh, there we go. And then 39.92. Now, why do we have evidence that children's cereal has more sugar than adults? Because the what is what? Why do we have more evidence, or why do we have evidence that the children's cereal has more sugar than adults? This is an important thing to know. Why do we have evidence that the children's cereal has more sugar than adults? Because the what is what? Actually, composite was 600. Oh, nice. Yeah, there is 201 on it. And we review stuff in later classes because the difference is positive. Since the difference is positive, the children's cereal had more sugar. The difference being positive means that the first mean is higher. And then also the interval does not contain what, which means we could reject that value. The interval, which when we test the null right here, does not contain what for the difference between children and adult cereal. It does not contain what value, which means we could reject it. The interval does not contain what value. So we could reject that value, which is the general null we use. The interval does not contain what value. What would be no difference? We're doing a lot of reviewing with this question of the output right here. So the interval does not contain what value, which means at the 0.05 level, because it's a 95% confidence, we could reject it with an alpha equal to 0.05. On the two-tailed alternative, the interval does not contain the value of what? What value does the interval not contain? It does not contain 0. So that means 0 is not a believable difference. So you can reject 0. Does that make sense, Lindsay? Like, you think the difference is somewhere that children's cereal has somewhere between 31 grams more sugar to about 40 grams more sugar. I'm just rounding it. So you think children's cereal has somewhere between that much to that much more sugar in it than adult cereal. So you would say, I reject that there is no difference. I have evidence of a difference. It's probably around 31.4 to 40 grams of sugar more. And we have very strong evidence of this to say that there is a difference. Also, we can reject the null hypothesis here at the 0.05 alpha level because 0 is not contained in our confidence interval. That's kind of a review of the whole chapter. This question right here really goes to understanding the jump output and what are we doing. So this is that the children's cereal has somewhere between this and this much more. Kind of a simple question when you look at what it requires, but I want to make sure you understand the theory behind it and what we're doing. So really good question right there. Make sure you understand the theory. I'm not here to just solve the problems. I want to make sure you understand what we are doing. What was the next question? Drop it in the chat. Drop that next question. It is your call if you're here right now. Which one should we do? There was the teaching method and another thing. Drop that next question. We did that one a lot yesterday. We did it twice. We did drinking last night too. Which one should we do? Core plus mathematics, teaching method. Go Cardinals! Yeah, go Cards! Shirt feels nice. I like it. Okay, this one right here. Here's two versions of this. This is the Core Plus Mathematics one. Is it Common Core? It's interesting. A lot of people... I don't know. I'd have to look. I don't teach math. I teach how to use math. I teach the reasons we do things. And that's what's important to me. It's not memorizing stuff. It's why do we do this? So they want to see if there's a what. Let's talk about why we do this. They want to understand if there's a what between these two teaching methods. So they've got teaching methods, CPMP, and they've got the traditional way to teach. And they want to see if there's a what between the two methods. So they look at the scores. They have some students go through, 320 students do the CPMP method. They want to see if there's a difference in the average scores of students, right? So if we conclude that there's a difference, we probably want to look to see which way the difference goes. So which alternative should we use if we're trying to investigate if there's a difference? A, B, C, or D? And if you read them, we'll read it once we figure out the answer. Should we use A, B, C, or D to figure out if there is a difference? Well, the null hypothesis is that there is no difference between the average score that says the true average score using this teaching method minus the true average score using this teaching method is equal to 0. There is no difference. That's the null. So the correct alternative to check to see if there is a difference would be what? The correct alternative to check to see if there is a difference would be what? They never indicate which way the difference goes, so we're just going to see if there is a difference. They don't indicate the sidedness of this. So B could be possible if we wanted to, and they don't go this way with the question, but I do agree B could be an answer, Lindsay, if you wanted to see what. And a good way that B won't be the answer, and I'll explain why here in a moment. They're just checking to see if there is a difference. But B, let me zoom in on it right here. With B, you would be investigating what? If you take this and put it right here, you'd be investigating what? That the average score using what is what? So this wouldn't test a difference. I mean, a difference of sorts, but not just a difference. This would give directionality to the difference. And this would be the right-tailed test, a right-tailed, one-tailed test, or a one-tailed, right-tailed test. So that would test what? Yes, it would be B if they were asking, well, so it'd be A if they wanted to see if it's lower. So A would test if it's lower, which is over there, but they want to see if there's a difference. So which one should it be? They want to see if there's a difference. So if they want to see if there's a difference, which one should it be? So if they want to see if there's a difference, which one should it be? Which doesn't give directionality to it. It's the two-tailed test. They want to see if there's a difference. And the null always has the equal sign, so that narrows down the choices a little bit here. So they want to see if there is a difference. Then it's D. Oh, psych! Lindsay right there, some 10,000 points practicing right here. So if it doesn't give direction, we go with the non-directional test, the two-tailed. This just says that the difference between these two methods is not equal to 0. So that would mean there is a difference. Does that make sense, Lindsay? Like the average score on this test minus the average score on this test, which is the difference between the average scores, is not equal to 0. So there is a difference. So the null is there is no difference between the average scores, and the alternative is there is a difference. This one would imply that it is lower for the first test because of the less than sign. You can just plug it right there. First test less than second test on average. This one would be the evidence trying to look for a first test higher than second test because you can just take that and plug it right there between to think about which way it's communicated. And we are looking for the difference. So now we need to do the T, which means we need to know our what. Let's call Leo right here. We need to know our what to solve this. What are we going to have to know to solve this? What are we going to have to know to solve this? I'll start writing it, and you start telling me what goes where. You got to know that notation.
Notation, brother.
Love it. So it's CPMP. It's the first mean and traditional. So what? Can anyone help me out with this right here? Some of these are going to be kind of easy. if you look at the formula which is given to you, and so what do we have right here? You got to help me out with this because this is the tough part. What do you have right here? I'll start marking it as we do it, but this is where a lot of people get lost on the problem, like finding the right formula, because this is the 2-sample t-test formula. So we're taking a difference up top. So this is a difference, and we're dividing it by the standard error, which is going to standardize it. So it's a difference divided by a standard error, because this whole quantity right here is the standard error, and that is just the difference between two means. So the test is going to take a difference and standardize it. It's going to give us a t with a complicated degrees of freedom formula. I think so. Yep. Great job right there. First mean minus second mean. And sample sizes should be easy. Sample size for first. And I don't know, we're running out of colors here. There we go. Sample size for second. No. Oh my gosh. There's sample size for second. And let's do some greens for these. I like blue. And last but not least, a little UT orange right there. And there you go. There's the plug and chug for the numbers that we can put them in and know where the means are at. The top is the difference between the means, and the bottom is the standard error. So we get 57.37 minus 53.91 over square root, not standard error. 32.09 over squared. Don't forget squared. I forgot that yesterday. 320 plus 28.45 over squared. Dun, dun, dun. You forget to square, you're going to get it wrong. 273. So, hey, Brian, I'm in another class, but I have a question about 10% between quiz. Yeah, Leah, which one are you wondering about? Drop it in the chat. We can maybe do it next year. Drop it in the chat. We'll see if we can get it done right here. Shouts to your other class. Divide by 320. There we go. There's that. 28.45 divided by 270. Oh, 28.45 squared divided by 273. Okay. Plus that and square root. 2.48. T is going to be close to 1. So 2.48. And once we find this t, what do we have to do next? Once we find this t, what do we have to do next? 3.46. What do we have to do next? Once we find this t, what are we going to do next? Let's check it out. Oh, we just did that one at the start. We just did that one at the start, Leah. Good question. We just did that one at the very start. It's in yesterday's video too. But we did it at the start. So plug it into the t to find the p-value. Exactly. Plug it into the t to find the p-value. Yeah. So this is going to be between 20 and 10%. The p-value is going to fall off quicker. So it's going to be about 3 decimals. That's going to be about it. I'll find it here in a second, but just looking at this p-value right here, would you reject? I'll figure out the exact one in a moment, but look at this right here. Would you reject or not reject the null? Would you reject or not reject the null? Look at the p-value, and I'll show you how to get the exact one in a moment. Would you reject or not reject the null? Would you reject or not reject the null? Reject or not reject? It's going to be a little higher. Reject or not reject? Look at the alpha level. When the p-value is high, let the null fly. When the p-value is lower than alpha, just let it go. Fail to reject. We fail to reject the null. And does that mean there is evidence for the alternative? No, you're not rejecting your null right here. Does that mean you have evidence for the alternative or you do not have sufficient evidence? If you do not reject, what would you have for the alternative? There is not evidence. So if you reject, it's because you have evidence. If you do not reject, there is not evidence. Do we get it right? Dang it. I get one more shot at this. Dang it. Was my first answer right? Dang it. Okay, let's go find the right answer. And Mariah, good to see you here too. So we're going to go find the right answer right here. We have to go to the t-applet, And the good news for us is it gives us the degrees of freedom here, which are 590.116. We're just going to enter in 590 on this. Let's go ahead here and enter in 590 degrees of freedom, which gives us the shape of the T. We're going to go ahead here and enter in our T value right here and do the two-tailed test. It's 0.164. So I was close-ish, but not close enough. 0.164, and that is the correct answer. Once again, you have to put in your degrees of freedom to control the shape of the T. There are infinitely many T's because they're based on degrees of freedom. So put in your degrees of freedom. And why am I not doing the left or right? Why am I doing the two-tailed? So why am I doing the two-tailed right here? Why am I doing the two-tailed? Why have I done the two-tailed? I've done the two-tailed because why? I've done the two-tailed because why? We did the two-tailed because of the what of the what. We've done the two-tailed because the what of the what. We're looking at not two samples because it's the two-sided. It's the two-sided. So it's not because we have two samples. It's because of this right here, the two-sided. So good practice right there. We're seeing if there is a difference, which is the sign of the alternative. So if I wanted to, and this is a good follow-up question, if I wanted to see if the second method or the first method was higher and I used the greater than test, what would be the p-value for the greater than test? So if I click right tail, what would be the p-value for the greater than test? This is a good check of knowledge. I like to throw additional things out here for practice. What would be the p-value for the greater than test? So think about it's just going to go to where we landed. Yeah, is it assignment 11? Which one do you want to do, Payne? We do it here a little bit. What would be the p-value for the greater than test? Tell me which portion to do and we can check that out. What would be the p-value for the greater than test? Who can figure that out in the chat? P-value for the greater than test. So you're going to go right here and go greater than this mark. I'll give it a few seconds here more for 10,000 points. What is the p-value for the greater than test? Give it a few seconds. Mariah, you're right. So what would it be? That's right, Mariah. This is the theory we need to know. This is the good theory. So go ahead and do that right there and be like, oh, the greater than test has this p-value. So the greater than test would have a p-value of, there you go right there, Caden, great work, yep. And these are the things you need to understand and know about p-values. The left tail test is going to be the complement, which is 0.918, and you can see it right there. So we can understand how this works, where you double this to get the two-tailed. The right tail is half of this, and then the left tail is the other side of it. So we can see how p-values are created, which are the same way they are created in jump output right here. Now, these are so tiny, it's hard to see the relationships because they're very, very tiny p-values. So you can't see that this one right here is the double of the smaller one. So, and then they're basically 0, so the complement is basically 1. So with that, let's take a look. The next question I think comes from Leah. Do consumers spend more at a trip to Target or Walmart? So do consumers spend more? Okay. And so 29, 4 to 3, stats will 1, chapter 17, quill. Do consumers spend more? Let's check it out. Here we are. Do consumers spend more? And always remember, try to understand the big theory components. There's the other new teaching method. Oh, where is it? Here we are. So let me remark this again real quick. 3023. So with this, we are comparing the what and the what. 1A through 1D. We do some start with question 1. So let me write that down right here. And y'all. Okay. And let me see. So do consumers spend more on a trip to... All right, I'll be right back, everyone. Right back. Hey everybody, we're back. Let's start up the pharmaceutical question right here. And let's take a look. Or the Target and Walmart question. Here we go. With the Target and Walmart question, suppose researchers are interested in the question collected a systematic sample of 82 Target stores and 78 Walmart stores. So customers, by asking customers for their purchase amounts, so what do they want to see? They want to compare the what right here. Tess, good to see you here. And Allie, good to see you. What do they want to compare? What is the point of this? And then look at this right here. So what are they trying to compare right here? What are they trying to compare? What are they trying to compare? So explain to me the context of this problem. They are trying to compare what right here? They're seeing if there's a difference between what? What do they want to compare? What is the point of the question? Really good stuff right here to think about. What are we doing? So is there a difference between the average amount that people spend at Walmart or Target, right? So is there a difference between the average amount that people spend at Walmart or Target? So what would be the null hypothesis? The null hypothesis would be that the difference is what? So the null hypothesis would be that the difference is what? If we talk about the average amount spent at Target and Walmart equal to 0. And the alternative would be that it is not equal to 0. They give us the degrees of freedom here, which is really nice of them. And then this question basically boils down to a know your what problem. This question basically boils down to a know your what problem. What is this question going to boil down to right now? That would be no difference. Great job right there, Mariah and Ali, and excellent work, everybody. Thank you so much. So, good stuff. And let's take a look right here. So we have here, I believe they're doing target is the first mean. So let's see, did they say it? Well, if we're doing there's a difference, it won't matter positive or negative. I'm going to go out on a limb here and say that target's the first mean. So we have y bar target minus y bar Walmart over square root s sub target squared over n sub target plus s sub Walmart squared over n sub Walmart. So now that we have all the notation on here, great job, Ali, right there, know your notation, we can start plugging in the values. So we're just going to start plugging in where we see the numbers. We have here 42 minus 54, and that's going to be a difference of 12. Now we need to standardize this difference right here. So we have 21 squared, got square root this whole quantity, over 82 plus 18 squared over 78, good. That's going to equal a t-statistic. How do you know which one to put first? It should tell you, but since we're doing the two-tailed test right here, the p-value would be the same either which way because we're going to reflect it. So I'm going to see if it actually gives it to us either way because the two-tailed test will reflect the result on the other side. Does that make sense, Caden? Maybe they realize it doesn't matter which way we subtract it. It is going to matter for the t to be positive or negative. But when we do the p-value, since we're reflecting it on either side, it won't matter if the difference is positive or negative 12, because if we did negative 12 standardized, it would still be the same p-value. No, really good question right there, because I was wondering that too, and I was like, as The Rock would say, it doesn't matter. It's not going to really matter for the p-value right here. They should generally tell you which one they want. Maybe they're just trying to help you understand, though, for these problems that wouldn't determine a different p-value, though. So it's going to be about a 1.27 or something, 9.532. And so this is the t statistic right here of 12 divided by that is 1.26. They probably wanted 2 decimals. 1.26 round to 2 decimals, 1.26. What's interesting, how are the degrees of freedom are really good. I can actually tell you the p-value for this one with pretty good certainty. The p-value for this should be about, let's go there. I'll show it right here on here because maybe people are wondering how I did it. Anytime you use the t, you have to know the what for the t. Anytime you use the t, you have to know the t's what. If we find a t, you have to know the t's what. Every time, to know the shape of the t, you have to know the what of the t. Anytime you use a t, you have to know the degrees of freedom, because the degrees, great job right there, Mariah. The degrees of freedom control the shape of the t. So huge points in the chat. The degrees of freedom control how the t looks. So we have to go back here and grab the 156 degrees of freedom. and drop them right there. And then our t statistic of this can go right here, and we do the two-tailed and the p-value. Oh my gosh, I should have doubled it. I didn't double it, so had I done it, new approach for teaching. I think we did that one. We did the new approach, Shannon. Check it out. We have that right here. Or did we do the new approach? We did the core plus mathematics one. Might need to take a look at the new approach for teaching, but yeah, we might have time to check that out. I think we're gonna do a little 320 after this. But yeah, good questions. So Brian did not get the p-value off the top of his head. It should have been this. So think about this. Is that p-value same result? Do you reject or fail to reject the null? What's your call right here? Reject or fail to reject the null hypothesis. So look at your alpha level. Look at your p-value. Is your p-value high? Just let the null fly. Great job, Ali, right there. So we failed to reject the null. Does that mean there is evidence for the alternative or there is not evidence? And great job, Ali, right there. So we failed to reject the null. There is evidence or there is not evidence for the alternative. Fail to reject the null, and that means there's not evidence. We don't, and they say sufficient, which is a good way of putting it. If we fail to reject the null, there is not. What in the world? Oh, no. What did I do wrong? Did I put the maths in wrong? Okay. Wow, that's the worst I've ever done on a problem in a long time. Wait, does it say they want to see if there is their test, supposed to research test to see if the means are equal? Where did I do maths wrong? This means we did the maths wrong. So let's look at the numbers here again. S sub 1 squared over n sub 2. It looks like all the maths are wrong at the end. What happened? 21 squared divided by 82. 18 squared divided by 78 plus this. What did I forget to do? What did I forget to do? Who sees it? 10,000 points in the chat. What did I forget to do? This is taking the difference between two means and standardizing it. So what did I forget to do? This right here is the standard error right here, Ali. Good questions. That's the standard error. So it's the difference divided by the standard error. I did divide it, but that 9.53 is not the right number. I didn't square root it. So now the t is going to be much what? Now the t is going to be much water. The t is going to be much water. 3.88, 3.89. The t is much water. 3.89. And the p-value is probably that. And that means we can reject there is sufficient evidence. That should be the way it goes now. P-value is going to be like this. Let's look at it. Really? No? Let's find out. Negative? No way. If you don't put the negative, just tell me. They do want the negative difference. So, sorry, this question threw me for a loop. I went and took some Dayquil for a moment. But this question right here definitely threw me for a loop. They do want the negative difference because they are taking Walmart minus... They don't say to use mean A as Walmart, right? That's not fair. I guess because they do reverse alphabetical. Usually when tests are done, they're done with reverse alphabetical. So it should be Walmart minus Target. If you entered in the positive one right here, it shouldn't matter. But once again, the p-value right here would be found by putting in the test statistic right here, the t. And this is so far off the curve. Like I said, if we do the two-tailed, it's basically 0. And it gave a nice plus or minus on it. How are people doing on this problem? I totally got this problem. Did it backwards. And it'll accept 0 right there. Check answer. And it should just accept regular old 0 for it, because it's very small. How are people doing on this problem? And Ali, I know you're asking questions about the formula. So on the review 3 sheet, let's go take a look at that real quick right here. On the review 3 sheet, let's go to the formula sheet. Thank you. You think it's good going through it? Good stuff. So here is the formula sheet right here. The standard error, which is what I've already written out, is the S1 squared over N1 plus S2 squared over N2. Bye, Mariah. Have a good day. And this is the difference right here. The difference is usually assumed to be 0. So if you compare this formula right here, this is the formula on the sheet. I don't want that highlighted. So here's the formula on the sheet. And going right here, let's look at my formula to it. So the difference is the top portion. Oh, no worries. This is the practice. So if you subtract two means, you're taking their what, Allie? Don't worry about this right here. If you subtract two means, that's what we assume the difference is equal to. If you subtract two means, you're just taking their what? If you subtract two means, you're just taking their what? If you subtract two means, you're just taking the what of the two means. That's the difference of the two means. And then any difference to make it into a test statistic, we need to take that difference and what it. To turn it into a test statistic, we need to take that difference, and this is the same quantity just written out. We need to take that difference and what it. Standardize it. And that leads to the test statistic right there. The formula sheet breaks down the standard error, just says standard error. This is not a formula right here. That is a notation. So that's just notation right there for the standard error of y bar 1 minus y bar 2, which is this quantity right there. So, and then it shows it on the formula sheet saying that quantity is this right here, saying here it is. So that is what would go right there. That makes more sense. Glad to hear that. So that is the hypothesis test. I prefer to write it out the following way, where we take the difference divided by the standard error. And yep. And then it's important to also know in the jump output, do you see where it says difference right here? Oops. Can you calculate the t statistic for me, Allie? Use the jump output on the screen to calculate. Sometimes we remove the t ratio. Tell me how using the difference and the standard error of the difference, which is that quantity right there, tell me how you would mathematically calculate this t ratio right here. Like use these numbers and see if you could find the t ratio, which is here in this output, which is the difference divided by the standard error. So you can see the same in the jump output to make sense of the formula. The difference between the two means, the standard error of the difference, which is this mathematical if you put in these standard deviations. So how would you find this t statistic here mathematically? How would you calculate that t statistic? To calculate the t statistic, we simply do what? The t statistic would be calculated doing what? Yep, and so it's going to basically be that. Jump might carry more decimals, and so literally what you're going to do is there's the standard error, and there's the difference. And if you divide those, you will get the t statistic. So dividing those gets you the t. Does that make more sense? Great job, Ali, right there. Can we do the core plus? Yeah, with the margin of error. Let's do one next here. Then I think we're going to do a little 320. Let's do the core plus with the margin of error. Good question to review. I like that one a lot for what it covers. So let's go find that core plus with margin of error. Core plus, you're welcome. This is a very good quiz. It's very challenging. Lots of good stuff right here. So the core plus with the margin of error. Okay. So how do we find the margin of error? Talk to me theoretically about the margin of error. Talk to me theoretically about the margin of error. The margin of error is what theoretically? So you always want to understand what the ME question. And the margin of error is what? Upper minus lower divided by 2, and that's half the length of the interval. Because the upper minus the lower is the top of the interval to the bottom. So if you had to guesstimate the standard error, the margin of error for this, we could do a teaching method. Just put the start of the question in here, Shannon. We'll do that one next, and we'll do some 320. Half the length of the confidence interval, right? So just give me a guess of the margin of error. Before we find it, just give me a guess. Don't just do it in your head. 5 and 11. Give me a guess of the margin of error. This, and we got to carry all the decimals. I messed this one up yesterday. 3, Ali, great job right there. 3 is a good guess because we could say 8.5 plus or minus 3. It's a really good guess right there, Ali and Caden. So you're on the right track if you put 3 as a guess because that's about half the length of the interval. So let's go upper minus lower divide by 2. And look, our answer is kind of close to 3. Great job, Ali, finding the exact answer. And we have to put in the exact rounded to 4 decimals. So we've done it right there. Great job, Lindsay and Ali. And then you just want to look at it and see if it makes sense. And your guess of 3 was very close to the right answer. If we were to make a 99% confidence interval, and think about how this goes, we made a 95, I believe. So if we go from 95 to 99, the confidence interval will get wider. If we go from 95 to 99, the confidence interval will get wider. And Shannon put the start of the question. We'll do it here next. It will get wider, 68, 95, 99. So the margin of error would be wider, larger, because the critical value increases. The critical value is the t statistic used to create the interval right here. So when you go from containing 95% of values, your t statistic is usually close to about 1.96, and it increases as you increase the confidence interval. New approach to method? Yes. Let's check it out here next. With 95% confidence, let's see right here. The average, because we're talking about means right here, using the CPMC methods, because we're doing big value minus small value, will do better than the traditional method by this amount. Now, why is it that the first mean is higher? This is something we've been reviewing today. Why would we have evidence right here when we look at the difference, evidence that the first mean is higher? Why would we have evidence, looking at this interval, that the first mean is higher? If you look at this interval, why would you have evidence the first mean is higher? You would have evidence the first mean is higher because the interval is completely what? So we would have evidence the first mean is higher because the interval is completely positive. The interval is completely positive, suggesting to us, what is your estimate of the difference between these groups? So if you had to estimate the difference, what would be your estimate of the difference? Does anyone have an estimate of the difference? This is a really good advanced question. So what is your estimate of the difference? Not 6-ish. The estimate of the difference would be the what of the interval. The estimate of the difference would be the what of the interval. The estimate of the difference would be the what of the interval. And let's take a look at the jump output to see how it looks. When you look at an interval right here, the estimate of the difference is the what of the interval. Look at the interval and look at the difference. It's towards the what of the interval. The estimate of the difference is at the where of the interval. Good things to know for this. The estimate of the difference is the what of the interval. The middle of the interval. Yep, because think we said, and we'll just call it 3. So what if I did 8.5 plus or minus 3? Does that basically construct this interval? 8, 8.5, somewhere there. Do you see 8.5 plus or minus 3 is 5.5 to 11.5? Now, that's not the exact value. If you want to solve the exact value, you would need to go here and average the two numbers. So you'd have to go to 5.5728 plus 11.4272 divide by what? No way, it's exactly 8.5? Wow. So exactly 8.5. Good guesstimate right there. Does the result suggest that there is a difference? Yes, the results do suggest there is a difference because the interval does not contain what? If there was no difference, the interval would contain this. Our interval does not contain it. So this suggests to me there is a difference because the interval does not contain 0. So it only contains positive numbers, which means it doesn't contain 0. We finally got 100 again. Just make sure to not make errors. That -1 I wouldn't care about. Let's go grab a new student approach, and we'll do some 320 here. Talking about their stuff. Okay, a new approach. A new approach for teaching that engages students. After field tests using 36 high schools over a 3-year period, researchers compared the performance of the new approach to those who were taught with the traditional curriculum. During the studies, students... Oh, we got to put the timestamp on this. Timestamp. Okay. During the study, students in both classes that used the new approach, traditional classes took an algebra test that did not allow them to use calculators. The accompanying table below. Are the mean scores of the two groups significantly different? We just found out the what here. What did we just find out right there? Are the mean scores significantly different? What did we just find out? We just found out the what of the what. Are they significantly different? Null and alternatives. So which of these is the right answer? A, B, C, or D? Are they significantly different? They want to see if there is a difference. So A, B, C, or D. Which one do you think? A, because the null is that there is no difference, and the alternative is that there is a difference. So the null hypothesis is that there is no difference, that the difference is equal to 0, and the alternative would be that the difference is not equal to 0. Do you think the assumptions are satisfied? I would say yeah. If the groups are independent, we need independent groups or independent means. Though it is not students were randomly assigned to each class, that'd be good too. Random assignment. And so random, 10%, nearly normal. Sample sizes are large enough, central limit theorem applies for nearly normal. We'd look to be good on that. Make sure to know, and I think we still have the notes open from yesterday, make sure to know all your conditions. We just kind of went through them quickly, but condition 1 right here being randomly selecting individuals. Condition 2 being less than 10% of the population. They don't mention that, but it's safe to assume that a couple 35 students are less than 10% of all students. And then you have to pause and you have to ask yourself, if it's categorical or quantitative? And since we're looking at a score on a test, that's quantitative, which means we go with the nearly normal. And both groups have to be nearly normal. And then the independent groups, which we went into more detail on yesterday, is the fourth and final condition. And we want the groups to be independent of each other. But then remember, and then we have there for Cat, great job, Ali. And for this one, there is a fourth condition called the independent groups, which means group A does not influence group B. Like when you send students to camp A versus camp B, they would not influence each other's scores. And then the last one right here, we would have here that it wouldn't work if we did a before and after test. So definitely review this from yesterday where we talk about independent versus dependent means, or things like with The Biggest Loser where someone's starting weight is very dependent on their end weight, or their end weight is very dependent. Refer to the computer output for the hypothesis test. Explain what the p-value means in context. And so the p-value here is very tiny. We're going to reject the null. There is less than a 1 in 10,000 chance that these results are no. The means for the two classes are actually no. If the means are actually equal, because this assumes the what. If the means are equal is to assume what is what. If the means are actually equal, that assumes the what is what. What do we assume when going into this test? If the means are actually equal, assumes the what is true. Go back here to start. If the means are equal, would assume the what is true, which is what we do for the start of a test. If the means are actually equals, assumes the what is what. So we say, given the null is true, then the probability of our observed result is this low. So what do you think? This starting assumption is probably what? Because what we saw is very unlikely given the null is true. So what do you think you should do here? Just think this is good practice on why we do it. So given the null is true, what you saw would only occur about 1 in 10,000 times due to random chance variation. So you should probably do what here, which they're going to get to at the end of this. You should probably do what here. So given the null is true, your results would only occur about 1 in 10,000 times. So you should probably do what here? So given the null is true, your results are very unlikely. You should reject the null. Because you'd be like, well, if the null is true, my results would be very unlikely. So I think the null is not true. I think there actually is a difference. So when we look at the difference here, the difference, is it positive or negative? And they're being really tricky. You can actually see that the means right here, traditional has a higher mean. I would go with that. So traditional has a higher mean. Let's take a look. On average, students who learn in the new class, no. On average, students who learn in the new class did significantly worse on the algebra test. That does not allow them to use calculators, and students who learn by the traditional. I think that's going to be it. On average, students who learn in the new method did significantly better. No. Students who learn in the traditional measure will always know. This is talking about individual students right here. We want to talk about on average. Let me look at the last one. On average, students who learn in the new class method will receive 29 on average. No. So we have evidence that the traditional method is actually better. We did test to see if there was a difference, but the test came back resounding that there's a very strong difference, and the mean of traditional is higher. So I looked at this right here. Also, the test statistic is negative, implying a negative difference, and they subtracted mean 1 minus mean 2, and you can see the mean is a lot higher. The best guess of the difference is how much? What is your best guess of the difference in scores? The center of your confidence interval would be what right here? Really good advanced question. The center of your confidence interval, what is your best guess of the difference between these? And just think about how you would do this if you didn't have statistics. If you had to guess what the difference was between these teaching methods, what would you guess the difference is? What would be your guess of the difference? Don't even think about statistics. Just be like, well, this one has a score of 29. This one has a score of 38.4. So my guess of the difference would be what? If I had to guess what the difference is, what would you guess the difference is? There's probably about a what difference in the tests. Not 4.7. Good guess is Blake right there. I would guess the difference between the teaching methods is what? I would guess the difference between the teaching methods on the average scores is what? This is good theory and understanding what you're doing. I would guess that the difference is equal to what? 10,000 points on the line right here. I would guess, not divide by 2. So I would guess that the difference is what? So think about the difference in teaching methods. So if you had to guess the difference in teaching methods, 9.4, because what did you do right here? 9.4 is just the difference in the average scores. So your best guess of the difference is that the difference is about 9.4. And if you look at the confidence interval, which I don't think we have the test to review open, the center of the interval is the what? The center of the interval here on the review sheet could be described as the what of the what. So let's go to the review sheet. The center of the interval is just the what. So Blake, you just did this right here, and that's just the what, which is your best guess of what it is. The center of the interval, which is your guess of the truth, is just the what, the difference of the means. So what's your best guess of the difference of the means? Well, and you could make the interval, but my best guess is that there's about a 9.4 difference. And then if we were doing this as a problem, we would go on to find the what for the interval. Like we don't have that right now, but if we were to do this as a bigger problem, we would have to create a what for that interval because we just guessed the difference right there. The difference is about 9.4. But then we need to give it a what to be like, because it's about 9.4 what. Because then we need to find the what of what we think the difference might be. Give it a what. Well, we would find the t statistic related to the percent confidence, and then we would create a margin of error with that using the standard error right there. So does that make sense, Ali? Hopefully this has helped your understanding and your knowledge of how to use these, because we're trying to say, like, which teaching method is better? Well, we think there's about a 9.4 difference, but we could also reject that there is no difference. So when we create this interval, it would not contain 0. So we could create the interval, and it would not contain 0 because we rejected it, the null hypothesis. So it would come to the same result. Yep. Understanding what you are doing is key. Like, why are we doing the difference between means? Well, we have test A and test B, or teaching method A, teaching method B, and we're seeing who scores better on the test. Going to look at more office hours too. Noise. We did some yesterday. Let's do a little 320 here to end. 320 in class. We're going to do some, if you stay tuned for this, you're going to see some really interesting stuff. Let's do some real fun 320 stuff. Fun 320. Getting other things going. Fun 320. And over class ratio. Nice. I have starting off 320's assignment. Assignment 11. Logistic regression. Logistic regression. Okay. So this is BAS 320, assignment 11. Let's go take a look at it. So we're here at 1, 2. When I started taking timestamps during teaching, my life got way better. Because I used to have to come in at night and do these. Assignment 11. Let's go take a look at it. Here we go. Time to do it. Okay. So if you're here for 320, what does logistic regression do? Now, does anyone know in 201, we'll throw some 10,000 points for all these answers. If we're doing regression requires what 2 kinds of variables? Regression requires what 2 kinds of variables? What is the first condition for regression? Q, straight enough. No outliers, plot doesn't thicken. So when we do regression in R, we do something like the following. I'm going to pull up some Survey 10 data and show examples of what we're doing. So this is regression. Height, weight, data, survey 10. That's the X, the Y, the X, Y variable, tilde X, comma data equals, and now we can see a visualize. If you look at this model right here, part of the problem with this model is probably that it's not linear enough. But what if I were to change this code slightly, and now we add in family equals binomial, and now we change the Y variable to a what? Gender is a what variable? So Blake, you're getting crazy points right here. Gender is a what variable? Gender is a what variable? Gender is a what variable? It's a categorical. Great job, Blake, right there. It's a categorical. So I shouldn't be able to do this, right? But what if instead of predicting gender, we predict the what of somebody's gender. So instead of predicting gender, we predict the what of somebody's gender, which is quantitative. This is how we're tricking it. The probability. So now it's a probability of being male based on your weight. You can see right here, I weigh about 190 pounds. I could actually go right here and actually add that to, I could go to AB line. We go here, it's a vertical line equals 190, col equals red. And you can see where I would be on here. That's where Brian would be, about an 84% probability, or somewhere in the 80s, it looks like. And if you were to be like 290 pounds, you'd be way over there at like it doesn't mean you're male, but very highly likely you're male. So this is the probability of somebody being male based on their weight. So this is what is called logistic regression. And there's an S name for this curve, like 90. Well, wouldn't be, so it would be not the percentiles of weights for males. Like, good answers, Blake, right there. I'm going to throw you some more points. It's not that that's your percentile of weight. It's your probability of being male. Does that make sense right there? It's not what percentile you are in weights. It's this person has this probability of being male, and we could actually solve the mathematics for it and figure out their probability of being male. So that is the person's probability of being male is very high, not the percentile of weight. So this is their probability when we predict how likely are you to be male. As you can see right here, if someone weighs more, they're more probable to be male. It doesn't mean they are male. It just means they're more probable to be male. Same thing with height. If we just change the height variable right here, you want to see a sad one, Blake? I definitely didn't help. There's height, and there's the height model, but watch this, GPA. What do you see this? If you have a higher GPA, what? If you have a higher GPA, what? So think about the way this is interpreted. Two people who differ in their GPA by 1 point, the person with the higher GPA is what? Two people who differ in their GPA by 1 point, the person with the higher GPA is what? So if we have two people, just grab two random people right here, and we'll go with the person with the 0 GPA, and we'll go with the person with the 1 GPA. The person with the higher GPA, person B, this is the interpretations. You could say that. You could say that. They're, I would say, less likely to be male because the probability of male is decreasing. I often like to phrase it 0 GPA. So two people who differ by their GPA in 1 point, the person with a higher GPA is less likely to be male. Does that make sense? So they are less likely to be male. The probability decreases as GPA increases. Sorry, I definitely didn't help with this model right here. Let's look at the questions and what it's asking. So we have different data. Fit a multiple logistic regression predicting if somebody clicks. Look at the summary. You'll notice many of the values are in A's. This occurs because of singularities. The model can't make estimates. Some variables like site category can be perfectly predicted, blah, 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 but it can't give. It is impossible to estimate. Examine the output showing the coefficients, p-values, and all this below. There we go. So just fit your model right here as we're doing. How do we add in all the variables? Meath, good to see you here. How do we add all the variables right here? We're doing it with different data, and we're doing the assignment basically. How would I add in all the variables, Meath? So how would I add in all the variables? Tilde what? And this, I think this will help out Peyton. We can't visualize it now. It just doesn't work for that amount of stuff. So now we have our model right here created, and we can see explicitly we really care about all the what's generally and all the what's. What is going to be the most important thing right here? We'd care about all the, what are the two big things to care about with this? I would say most importantly, I care about all the what's and all the what's here. The two things I'm usually going to look at first off are my what's and my what's. Like, what would you look at in this output right here? Now, there's more below. Not too much. I don't talk about null deviance. The sign, I like that. The sign of the coefficients, that's going to indicate that height right here, two individuals who are otherwise identical but differ in their height by 1 inch. The person who is taller is more likely to be male. The p-value actually tells us that height is not statistically significant, but weight and desired weight are. You know what's really interesting? Weight has a negative coefficient that two people who are otherwise identical but differ in their weight by 1 pound, the person who weighs more is actually more likely to be female. But take a look at this. Desired weight. Two people who differ in their desired weight by 1 pound, the person who wants to weigh more is more likely to be male. And actually, GPA comes back not statistically significant with all the other x's in the model. So you can see right here that due to probably the multicollinearity, all the x's in the model, GPA does not give significant variation to explain the y variable. We have things like number of body piercings coming back significant, video games coming back significant, but the big ones are going to be body piercings. How much do you want to weigh? How much do you weigh? Those are the only, do we miss one more? Video games, piercings, desired weight, and weight. Intercept, no one cares about the intercept. And this is barely not significant. Two people who are otherwise identical, where one person believes they're more attractive than others, then the other person, the person who thinks they're more attractive, is more likely to be male. Let's look at the questions. We just did some interpretations of coefficients right there, so that might help. When we compare ads on the same site, viewed on the same app, on the same device, otherwise identical ad, which position and what could we look at right here? Now, this is where it gets tricky. Who is the most likely person to be male when it comes to handedness? So I'm doing part B here. Who is the most likely person to be male? This is super tricky with these coefficients especially. Who is the most likely person to be male? People who are what? Left-handed. And the coefficients are really close. They have the same E, but this is the biggest coefficient. Then who's the second most likely to be male? So two people who are otherwise identical, but one is left and one is ambidextrous. The people who are left-handed are most likely to be male, more likely to be male. Not most, but more likely. Now, the next most likely would be what? And then right. And then if you had to give me a coefficient for ambidextrous, what would... Now, it doesn't really have one, which is the hint. But what would the coefficient of ambidextrous be? Because it doesn't have one. So what is the coefficient of ambidextrous? It'd be 0. So that's because it is the what level. And Meath, great work right here. Ambidextrous, just like this question up here. So we're doing an analogous type question. Ambidextrous is the what level for a categorical variable in the model. It's the reference. So you need to think about your interpretation right here of this to think about which one of those is more likely to click through. And what you probably want to do is you want to know the level of interest. So if we're predicting click-through rate, would we be predicting somebody clicks yes or somebody clicks no? If we are predicting click-through rate, would we be predicting click yes or would we be predicting click no? Would we predict click yes or would we predict click no? What would be the level of interest in logistic? In logistic, the level of interest is what? What would we predict right here? Would we be predicting probabilities of yes click or no click? Yes, and why, Meath? That's exactly right. We'd be predicting somebody clicks yes because it's the last one. In logistic, the level of interest is last. So if there's a positive coefficient, that means it what's like two things that are otherwise identical. If the coefficient's positive, those people would be what? So two individuals who are otherwise identical, if the coefficient's positive, those individuals would be what? So if the coefficient is positive in the model, those individuals would be what? Two individuals who are otherwise identical if the coefficient is positive. So yeah, for this one, yeah. And for this one, more likely to click, right? So for our problem, more likely to be male, more likely level of interest, right? And then for this one, more likely to click. So just depends. Are you predicting male? Are you predicting click? So that's exactly right there. Does that all make sense? Like more likely level of interest. So what's the level of interest? If we're making a probability of male, more likely to be male. If we're doing probability of click, more likely to click through. So good stuff right there. Question C. When comparing ads in the same position on the same site visit viewed on the same device, which device model, you may ignore 13 because it couldn't get a coefficient due to singularities, has the highest and lowest probabilities of clicking through? So how would you do this? How would you do this? Like, don't say which ones, but it's the difference in probability statistically significant. In other words, yeah, it literally tells you how to do it right there. How would you do this? How would you figure out which devices are the most likely and least likely, which basically gives it away, but don't say which devices, but how would you figure out which, like we figured out right-handed people are the most likely to be, left-handed, excuse me. Left-handed people are the most likely to be male because it has the most what. So we figured out left-handed people are the most likely to be male because it has the what. For that variable, it has the what. Most positive, largest coefficient, and then we could do the least likely by finding the negative. But do be careful. If you're figuring this out, you should always remember the what level. If you're figuring this out, you should always remember the what level. Do not forget the what level, which has a coefficient of 0 technically. Like, it doesn't have one, so it has a coefficient of 0. Do not forget the reference level, because it could be the reference level is the least likely, or it could be the most likely if all the coefficients are negative. If all the coefficients are negative, reference level is most likely. If all the coefficients are positive, reference level is the least likely. So do remember the reference level is the first alphabetical that you do not see in the output. What does this test right here tell us? So the drop 1 drops one variable. So why does degrees of freedom equal to 2 for handedness? Because handedness had what? Why does degrees of freedom equal 2 for handedness? Why does degrees of freedom equal 2 for handedness? Had 2 indicators. So the amount of indicators it brings to the model, and you have to run it if it has 2 indicators because you're removing both of these and doing a partial f-test with and without the variables in the model to see if it brings with it new variation. Does handedness bring with it new variation? Exactly. Handedness does not bring with it new information. We could technically remove it from the model. So handedness is not statistically significant as a variable itself. Why don't we just look at the summary up here? Like, why can't we just look at this, Meath? Why can't we just look at these p-values right here to see if handedness is significant? Because those are the significance from the what, which is not the significance of handedness. That's not the significance of the variable handedness. That's the significance of the what's for the what's from what's. Those significance right there doesn't tell us if handedness is significant. That is the significance for the what's from the what's, which is arbitrary. The significance from the reference level, which is completely arbitrary. So we don't look at those because this tells us is left significantly different from ambidextrous, is right significantly different from ambidextrous, and that's really not that important to us right there. We want to see, does the variable as a whole bring with it new information? I think we just did that one. Is the model better at predicting clicks than the naive model? Really good stuff right here, which we'll be talking about today. So what is the naive model? If you had to look at a table, of the click-through rate, or let's look at a table of male, would you predict everybody, Salikov, would you predict everybody here is male or everybody is female? Just looking at that data right there, would you predict everybody is male or everybody is female? And then we'll talk about what the naive model is for this, for categorical data. What would you predict if you had to look at this right here? Would you predict everybody is male or everybody is female? What would you predict? This is how to do the naive model. What would you predict? And why? That's exactly it right there, Blake and me. And why? You're right. Let's throw some more points. Why would you predict everybody is female? If you could only say everybody's male or female, why would you do this? And you're figuring out how the naive model works for categorical data. Why would you predict female? That is the right answer. So why would you predict, if I had to guess one, I'd say someone's female. Because why? This is how the naive model works. It's what's called the majority level. So most people are female. Exactly, most people are female. So if you had to guess one, you'd just say, well, since most people are this, I guess everybody's it. I mean, so think about that. In the naive model, you do not use any what's. It's the no knowledge model, so you don't use any what's. In the naive model, you do not use any of your what's. Because you're just saying, well, most people are females, Y variable, so I guess everybody's female. So you don't use any of your what's in the naive model. Once again, most people are female, so I guess everybody's female. I never mentioned any what variables. This is how the naive model works. The naive model doesn't use any of the X's. Does that make sense, Meath, right there? The naive model uses none of the X's. So you're just saying most people are females, which is the Y variable. I guess everybody's female. So how many people would you get wrong out of the total? So how many people would you get wrong out of the total? If you use the naive model, can you solve the mathematics? Here's this if you want to do it. How many people would you get wrong? What percent would you get wrong, which is misclassification rate? What percent would you get wrong? You talk about how the math, but in this case, male and female are not levels in the category. Yes. So you want to look at click-through and look at what's the most common click-through rate and then say everybody's going to do that. Does that make sense there, Meath? You'll be like, well, most people do this, so I guess everybody does it. Yep, you'd get about 45% wrong because you'd say all those males are females. Does that make sense? But let's look at our model. Our model does the following. If somebody is actually female, we should do what? If somebody is actually female, we should do what? If somebody is actually female, we should what? If somebody is actually female, we should do what? If somebody is actually female, it would be good to what? So if somebody is actually female, we should what? Our model should what? If somebody is actually female, we should what? If somebody is actually female, it'd be great if our model would what? The model should predict they're female. If somebody is male, our model should predict they are male. If somebody is predicted male who is female, that would be a misclassification. Or if somebody's predicted female who's actually male. How many people were misclassified by this model? How many people were misclassified by the model? How many people were misclassified by the model? So how many were total misclassified? What's the total misclassification rate of this model? 14. What's the misclassification rate of this model? What's the misclassification rate of this model? What is the misclassification rate of this model, which is the percent misclassified? And you can show me the mathematics. There you go right there, Meath. Does that make sense? So 14 out of 699 people were misclassified by the model. Now you could actually create the naive model over here from this output. Teaching to the test moments. Because this is just the distribution of the what? Take a look at what I'm showing you. That I'm putting in the box right there is just the distribution of the what. So we could figure out the naive model from this. That's just the what. Definitely test questions right here. That is just the distribution of the what. So that we're not looking at what the model predicts now. We're just looking at this. And you could figure out the naive model because that is just the distribution of the what variable. Yeah. That is just the distribution of the what variable. That is just the distribution of the y. That's the people who are actually male and actually female. So how would you get the misclassification rate right here? This is the larger number and the smaller number. What could you do mathematically to find the misclassification of the naive model right here? So show them the way to calculate using the actual who are male and the actual who are female from this output to calculate the misclassification rate. Like just write the equation to show like, okay, that's what the y variable is. Let me just look at the distribution of the y and use the non-majority class to find out the misclassification rate. So what would be the misclassification rate of this model using this output mathematically, which is about 45%? What would it be mathematically? Good checks of knowledge right here. So think about how to mathematically find the misclassification rate. Yep, that's exactly it, Meath, because that's going to be the smaller of the two numbers. So if you do that right there, you will divide by the total and row, and you will get about 45%. And this is the classification or the accuracy of the model. So it gets 55% correct and it gets about 45% wrong. And you could put the full numbers in the chat or the full numbers in your output. Yeah, some wine data set predicting quality. So just one more problem down here. Not too crazy, not too long. But Meath, does this look a lot better? Some check regression, which we'll talk about today. I guess I'll mention that briefly right here. Check regression sees that the logistic curve is the right curve to be using. And the answer is, does this check regression here come back good or bad, Meath? Does this check regression, what do you think about that one? Does this check regression right here come back good if we look at this one? Is that good or bad for a check regression? Is that good or bad? That's good. And how about this one? Is that good or bad? There's actually, we're running two different ways of doing it. We have two methods of checking it. Method 1 of checking it said it was good. Method 2, which is just another method, another way of doing it, said it was what? Bad. But how bad? Really bad or just a little bad? How bad? Really bad or just a little bad? What do you think? Really bad or just a little bad? Little bad. And if you were to keep running tests, eventually you would find a p-value below 0.05, right? Like if you just ran a bunch of tests, 0.05 occurs about 5% of the time or something at or below 0.05. So what do you think right here, Meath? What do you think I would do as a statistician if I saw this? Do you think I would be like, oh no, or like, eh? Do you think I'd say, uh-oh, low p-value, we got to reject the null, can't use the model, because the null hypothesis is that the model is a reasonable reflection of reality. And the alternative that we're seeing if there's evidence for it here is that the model is not a reasonable reflection of reality. No, don't burn it. This one doesn't give plots. This one doesn't give plots. You would if so in the logistic you don't get plots, but that is the right answer for quantitative models. Logistic doesn't give us plots, so since it's kind of meh, I'd say it's okay. It's like that's not super bad down here. Like that one's good, that one's kind of meh, and we don't like that, but you know, doesn't look like it's horrible. With that, we'll be teaching her in 13 minutes. Meath, did this help out a good bit right here? We did half the assignment talking about stuff. Just some extra predictions right here on how to make models. Going through predicting low quality of wine, talking about the shape right there. Good to see you here, Blake. Yep, awesome. Well, check this out and make sure you know how to do logistic. It's super important. Let's throw everyone some more points and 10,000 points. We've been going crazy. Want people here at the end to practice. Great job, Meath. We'll be teaching here in 12 minutes. Bye for now, everyone. Bye.